So in this lecture, I will discuss Borel-Cantelli lemma. Throughout this lecture, there is a probability space, omega f and p, which is fixed. And I'll start with some notation. So we will consider a sequence, En, of elements of the sigma algebra, En, f, and I will represent by the limit sup in N of this sequence N the following set. So for all n larger than 1, I take the union for all m larger than m of Em. As you see, since the sets En belong to F, this set also is an element of F, and I will represent by the limit inf of En the following set. Well, there exists n larger than 1 such that for all m larger than n, Em occurs. So this is again an element of F. And I leave it to you to check that the limit inf of En, it's included in the limit sup. So we defined the limit sup by this formula. Now I want to prove the following observation, that the probability of the limit sup of En, that this is equal to the limit in N of the probability of the union for m larger than n of Em. So I claim this is true, so let's prove this. And to do that, let me introduce the definition of Fn, which will be this set. So Fn will be the union for m larger than n of Em. Now observe that if I fix n, I can write Fn as En union, well, the union for m larger than n plus 1 of Em. This later set, by definition, it's Fn plus 1. So this is actually equal to the union of En and Fn plus 1. And this proves that, well, Fn contains Fn plus 1. So Fn plus 1, it's contained in Fn. And this shows, therefore, that the sequence Fn is decreasing. So the sequence of sets Fn is decreasing, and it decreases to its intersection. And we have seen that if a probability, a measure, it's finite, and in our case we are working with a probability which is a finite measure, we have seen that in this case we know that the probability of the intersection of Fk it's equal to the limit of the probabilities of the sets Fn. And this is exactly this identity, because recall, Fk is the union for m larger than n of Em, or m, the union Fk, the union of m larger than k of Em, which is exactly the limit sup. So this set here is the limit sup, and on the right hand side you have the limit of Fn, but this set here, it's exactly the set Fn. So we proved this identity. A similar identity holds for the limit inf. So recall that the limit inf is given by this formula. So I leave it to you as an exercise to show that the probability of the limit inf of En, that this is equal to the limit as n goes to infinity of the probability of these sets, which is the intersection for m larger than n of em. So I leave it to you as an exercise, but the argument is exactly the same. Now, limit sup, let me write again, the limit sup in n, it's equal to the intersection for all n of the union of em. What I want to prove now is the following, that take an omega, a point in the set omega, it belongs to the limit sup of en if and only if there exists a sequence np such that np is smaller than np plus 1. So this is a strictly increasing subsequence or subsequence of the original sequence such that omega belongs to E np for all p. So with that, I want to say that this set limit sup represents the set of points for which omega belongs to an infinite sequence of subsets. So omega, a point, belongs to the limit sup if and only if it belongs to infinitely many sets En. So let me prove this identity. Say that, let's prove first that if W omega belongs to this set, then we can construct such a sequence. And well, let's start with E1, the set En1. So let's assume that omega belongs to the limit sup. Well, this implies that omega belongs to this intersection. But if omega belongs to this intersection, it belongs to this intersection, to the set here with n equal to 1. So omega belongs to m, to the union for m larger than 1 of em. And if it belongs to this union, this means that there exists m larger than 1 such that omega belongs to em. Well, and call this m n1. So n1 is this integer m such that omega belongs to em. So in this way, we constructed our first index n1. Note that omega indeed belongs to en1. And now I want to construct by induction our sequence np. So I will assume that we constructed already the first p terms of this sequence. So we construct n1, n2, np such that omega belongs to enj for j between 1 and p. And now I want to construct the next term of this sequence. So let's recall that omega belongs to the limit sup. Since omega belongs to the limit sup, this means that omega belongs to this intersection. Since it belongs to this intersection, it belongs to all. So it belongs to all such sets. So let me take here n to be np plus 1. So I know that omega belongs to the union for m larger than this set np, this index plus 1 of em. And since it belongs to this union, this means that there exists m, well, larger or equal than np plus 1, which means m larger than np, such that omega belongs to em. Now let's define np plus 1 to be this integer m, which we just found. Now we have that np plus 1 is strictly larger than np, and indeed omega belongs to np plus 1. So in this way, by induction, we construct this increasing sequence np such that omega belongs to enp for all p. So we just proved that if omega belongs to the limit sup, this means that omega belongs to an infinite number of sets em. So now I want to prove the converse implication, and for that I will assume that omega doesn't belong to the limit soup, and I'll prove that I can't find this sequence. So let's assume that omega does not belong to the limit soup. So it belongs to the complement, and the complement, it's equal to the union of the intersection of the complements. And since omega belongs to this union, this means that there exists an n0 such that omega belongs to the intersection for m larger than this n0 of em complement. So it belongs to all of them, so this means that omega belongs to em complement for all m larger than this integer n0, which means that omega does not belong to em for all m larger than n0. So this means that, well, starting from n0, omega does not belong to any of these sets em, and therefore there can't exist such a sequence, because while starting from n0, omega doesn't belong to em anymore. So we are not able to find an infinite sequence, increasing sequence, for which omega does belong to enp for all p. Which means that, well, if this assertion is false, then this one is false, and that proves the converse assertion of the claim. So here it's the definition of limit soup. Let me call limit inf. Recall that it's the union for all n larger than 1 intersection of all m larger than n of em. So let me just state a few more observations. I already asked you to prove that the limit inf of en is contained in the limit soup of en. I also ask you now to show that if you take the complement of the limit inf of en, this is equal to the limits, the complement of this set, it's equal to the limit soup of the complement of the sets en. So you have this identity. We also have an interpretation of the limit inf. So omega belongs to the limit inf in n of the set en if and only if there exists n0 larger than 1 such that omega belongs to em for all m larger than n0. So this means that omega belongs to the limit inf if and only if it belongs to all sets em starting from one index n0. So I ask you to prove these three statements, and since we proved that omega belongs to the limit soup of en if and only if there exists this sequence np which is strictly increasing and such that omega belongs to enp for all p, I will write limit soup en as saying that, well, en happens infinitely often. So instead of writing limit soup, it's common to write this event as en happens infinitely often because, well, we just proved that it belongs to the point belongs to the limit soup if and only if it belongs to infinitely many sets en. So en infinitely often. And now we are ready to state the first main result of this lecture. So theorem, let's consider a sequence of sets En in the sigma algebra. And what I claim is that if the probability of En is summable, so if the sum for n larger than 1 it's finite, then the probability that the set En happens infinitely often, that this is equal to 0. And the proof, it's quite simple. So remember, En infinitely often is we want to estimate the probability that the intersection for n larger than 1 of the union for m larger than n of En. So this is the limit sup, which is the event that En happens infinitely often. And we have seen that this probability is actually equal to the limit as n goes to infinity of the probability of the union. Now we can estimate the probability of this union by the sum of the probability. So this is bounded by the limit inf in n of the sum for m larger than n of the probability of En. Well, but since this sum is finite, this means that as n goes to infinity, this sum converges to 0, and therefore this limit inf, it's a limit and it's equal to 0, and this proves that indeed the event that En happens infinitely often is equal to 0. Note that we did not assume the sets En to be independent. So this result can be applied to any sequence of events En. So let me give you an application of this result. Let me consider sequence Xn of IID random variables. And let me assume that they have finite fourth moment, so that the expectation of X1 fold is finite. Then what I want to prove is that X1 plus Xn, so the average, converge almost surely to the expectation X1, which maybe I'll call that M. So what I want to prove is that, well, if we have a family of IID with finite fourth moment, then the average converges to the expectation almost everywhere. And let's prove that. So first, let me simplify, and let me call Yj to be Xj minus M, the expectation of X1. So the random variables Yj are IID, and now they have an expectation which is equal to 0. So they have mean 0, and they are IID, and they also have a finite fourth moment. And in order to prove this, what we need to prove is that Y1 plus Yn divided by n converge to 0 almost surely. So this is what we want to prove now. Well, let me first remark saying that Zn, so this is a remark, Zn, a sequence Zn, converge to 0 almost surely. Well, by definition of convergence, almost sure convergence, this means that for all epsilon positive, so you have to go back to the definition of almost sure convergence, but we have seen that proving that the sequence converges almost surely to 0 means that for all epsilon, the probability that for all n larger than 1 there exists m larger than n such that Zm larger than epsilon, that this is equal to 0. So saying that Zn converges almost surely to 0 is to say that, well, the probability that for all n there exists an m such that this happens, that this probability is equal to 0. And now you recognize here the set that Zm it's larger than epsilon infinitely often. So if you want to prove that Zn converges to 0 almost surely, what we have to show is that the probability of the event that Zn it's larger than epsilon infinitely often has probability 0. So this is what we need to prove. So in our context, Zn is the average of the y's, and this is so what we need to prove. Let me erase and let me state what we need to prove. What we need to prove is that the probability that y1 plus yn divided by n it's larger than epsilon infinitely often, that this probability it's equal to 0. Let me call so these events event En, and this needs to be proven for all epsilon larger than 0. So let's fix an epsilon and let's try to prove this statement. Well, we have seen in the theorem that in order to prove that this statement happens, that this probability is equal to 0, it's enough to show that the probability of En is summable. If you are able to prove that this probability is summable, so that this sum is finite, by the first part of the Borel-Cantelli lemma, which we just stated, we get that the probability of this event is equal to 0. So what we really need to prove is that this sum is finite. So now let's replace En by what it is. So what we need to prove is that the probability of y1 plus yn divided by n is larger than epsilon, we have to show that this sum is finite. In order to prove that this sum is finite, let's apply Chebychev inequality, and you see that Chebychev inequality is really useful because we applied it a few times now. Let's apply Chebychev inequality first by taking fourth power on both sides and then applying Chebychev inequality. So this is bounded by 1 over epsilon to the power 4, sum for n larger than 1 of the expectation of y1 plus yn to the power 4, and this is divided by n to the power 4. Now let me compute these expectations. So here we have a fourth power, so there will be many different types of terms. There will be one term in which only one yi to the power 4 appears. So I'm expanding this square and I'm just classifying the different types of terms which appear in this expansion and counting them. So the first type of term, it's, you have fourth power here inside. There are n terms of this type, and they are all equal because the random variables are identically distributed equal to the expectation of y1 to the fourth power. So now there may be two types of different terms with inside the expectation. So we have yi and yj. So there is a fourth power, so either we have to the power 3 and the other one to the power 1, or we have yi square, yj square. Right? So since the random variables y are independent, this expectation it's equal to the expectation of yi to the power 3 times expectation of yj. Here I is different from j, right? Otherwise we are in the first case. And since y has mean 0, this term it's equal to 0. On the other hand, also by independence, this is equal to the expectation of y1 square to the square. So this is a finite term, and how many terms of this type there are? Well, you can compute. There are order n squared terms of these ones, and if you compute it carefully, there are 3n times n minus 1 terms. So up to now, we consider the case in which we have one type of term or two types of terms. So now let's see the case in which you have three types of terms, yi, yj, yk. Since it's a fourth power, one of them will be to the power 2. And in this case, again, by using independence and the fact that the random variables y have mean 0, you get that this is equal to 0. And here I'm assuming that I is different from j, which is different from chi, and I different from k. So all these types of terms will give you 0 contribution. And there is the last type of term, which is yi, yj, yk, and yl. And this term will also give you 0 contribution due to the fact that these variables are independent and have mean 0. So there are only, in this expression, there are only two types of terms which are contributing. These ones in which I have n, and these ones in which I have n minus 1. So this means that this expectation it's bounded by a finite constant times n squared. Right, because we have here finite constants times n, which is bounded by this expression, and here a finite constant times n squared, which is also bounded by this expression. This means that this sum, it's bounded by some constant divided by epsilon to the power 4, the sum n larger than 1, and here we have n squared divided by n to the 4th. This is n to the power 2, and this is finite. So we proved that this probability is finite. Since this probability is finite, by Borel-Cantelli lemma, this event, the probability that this event happens infinitely often is 0. Since epsilon it's any positive constant, this means that the average of the y's converge to 0 almost surely, and therefore that the average of x converge to m almost everywhere as we claim. So this is a very nice application of the first part of the Borel-Cantelli lemma. We get that, well, immediately that if the variables have sufficiently large finite moments, we get a convergence, an almost sure convergence. Remember that we proved convergence in probability if we had a second moment finite. Now we just proved that if the fourth moment is finite, we have convergence almost everywhere. So now let's state and prove the second part of the Borel-Cantelli lemma. Consider again a sequence En of elements of the sigma algebra F, but now assume they are independent, that these events are independent. And now what I claim is that if the probability that En, that this sum, it's infinite, then the probability that the En will appear infinitely often, will occur infinitely often, then this is equal to 1. So before we proved without the assumption of independence that if the sum is finite, then that the probability that En happens infinitely often is 0. Now, with the extra assumption of independence, if this, what we prove is that if this sum is infinite, then En happens infinitely often with probability 1. So let's prove that. So remember, En appearing infinitely often is the probability that for all n larger than 1, there exists m larger than n such that Em occur. And we want to prove that this probability is equal to 1. Well, actually, what we will prove is that the complement has probability 0. So what we want to prove is that the probability that the union for n larger than 1 of the intersection of m larger than n of Em complement, that this is equal to 0. This is what we are going to prove. And we have seen that this probability, so let's estimate this probability, we have seen that this probability is actually equal to the limit in n of the probability of the intersection of the complement. So we want to show that this probability is equal to 0. So let's fix n and let's consider this probability. What we are going to use here is that these sets are independent and therefore that the probability of this intersection is equal to the product of these probabilities. So I want to estimate this probability. And this is equal by independence to the product of the probabilities. Now, the probability of the complement, it's 1 minus the probability, so this is equal to the product of 1 minus the probability of Em. And now, in order to estimate this expression, let's recall that 1 minus x, it's bounded by exponential minus x for x larger or equal to 0. Remember, you have exponential minus x, this is 1, which is converging to 0 exponentially fast, and then you have 1 minus x, which is linear, and therefore 1 minus x, it's bounded by exponential minus x. So this is equal to m larger than, it's bounded, sorry, by the product of exponential minus the probability of Em. Now we have a product of the exponentials. This is equal to the exponential of minus the sum for m larger than n of the probability of Em. Well, but since this sum is equal to plus infinity, and since the first n terms can contribute only with n, this means that this sum is also equal to plus infinity. And it's equal to plus infinity, therefore exponential of minus infinity is equal to 0. So we just proved that for all n, this probability is equal to 0, and therefore the limit is equal to 0, which proves that the probability of this event is equal to 0, which yields that the probability of this event is 1, which means that En happens infinitely often with probability 1 if the sets En are independent and if the sum of their probabilities is equal to plus infinity. So let me make a remark before we continue. Let's assume that we have a sequence En of independent sets. We just proved that if their sum is infinite, then the sets En happen infinitely often with probability 1. By the previous result, which was not requiring that the n to be independent, if the sum is finite, then the probability that En happens infinitely often, it's equal to 0. So assume that the sets En are independent. We have a dichotomy. Either the sum is equal to plus infinity, in which case En happens infinitely often with probability 1, or the sum is finite, in which case the probability that En happens infinitely often is equal to 0. So we have here a first example of a 0-1 law. In the case in which the sets En are independent, the event En happens infinitely often has only two possibilities. Either it's equal to 0, it's equal to 1, and it's equal to 1 if and only if this sum is infinite. The other case, it will be equal to 0. So we have here a first example of events whose probability are either equal to 1 or equal to 0, and the sum determines if the probability is 1 or 0. So let me give you an application of this last result. Let's assume that we have a family Xn of ID random variables, and let's assume that the expectation of the absolute value of x1 is equal to plus infinity. So these random variables are not integrable. And what I claim is that the probability that xn is larger than n infinitely often happens with probability 1. So if the expectation of x1 is plus infinity and these variables are IID, then infinitely often xn will be larger than n. And the proof of this is trivial. We have seen that in order to prove that, it's enough to show that the sum that xn, the absolute value of xn is larger than n, it's enough to prove that this is equal to plus infinity. Right? Because these random variables are independent, and therefore these events are independent, and Borel-Cantelli tells us that in this case, this happens with probability 1. Well, but this probability, so let's prove that this probability is equal to, this sum is equal to plus infinity, but since the random variables are independent, this probability is equal to the probability that x1 is larger than n. And we have seen in a previous lecture that this sum is finite if and only if the random variable x1 is integrable. So since we are assuming that the random variable x1 is not integrable, this means that this sum is plus infinity, and therefore we proved what we wanted. And from Borel-Cantelli, we have that the probability of this event is equal to 1, which means that the probability that xn, the absolute value of xn larger than n, happens infinitely often. The probability of this event is equal to 1. So we just proved that if I have a sequence of IID random variables xn, such that their expectation, the expectation of the absolute value is infinite, then we proved that xn is larger than n infinitely often with probability 1. I want to show that this implies that the following event has probability 0. I want to consider the sets of omegas such that x1 plus xn divided by n converge to C, where C is a real number. So consider the sets of all omegas such that this average is converging to some real number. And I want to prove that this probability, the probability of this event, is equal to 0. I leave it to you to check that this event belongs to the sigma algebra F. So, in order to prove that this event has 0 probability, let me first claim the following, that this event, so the event that x1 plus xn divided by n converge to an element C in R, that this event is included in the event of all omegas such that xn divided by n converge to 0. So I want to claim that if omega belongs to the first set, it belongs to the second. So let's consider omega in the first set. This means that, and let me write it, x1 omega plus xn of omega divided by n, that this is converging to some C. So there is a C which depends on omega, and this C it's an element of R, such that this average is converging to C of omega. This is the definition of this set. Well, if this is true, then if I take x1 of omega plus xn of omega and I divide that by n plus 1, well, I claim that this converge also to the same C of omega. And this is clear because this fraction can be written as x1 of omega plus xn of omega divided by n, multiplying n divided by n plus 1. The first term converge to C of omega by, because we are taking an element of this set, and the second sequence converge to 1. So it's true that if omega belongs to this set, then x1 omega plus xn omega divided by n plus 1 instead of n also converge to C of omega. So now we know that this sequence converges to C, that sequence converges to C, so their difference, x1 plus xn of omega divided by n minus x1 of omega plus xn minus 1 of omega divided by n, this sequence has to converge to 0 because the first one converged to C and the second one also converged to C. But the difference, it's exactly xn of omega divided by n. So we just proved that if omega belongs to the first set, it belongs to the second set. And therefore, in order to prove that this event has probability 0, it's enough to prove that this event has probability 0. So what I want to prove is that probability of that xn of divided by n converge to 0, that this probability is equal to 0. So this is what I want to prove. So this is the set of all omegas for which xn of omega divided by n converge to 0. So this is what's represented here. So I want to transform this event in events which I can compute the probability. So I claim that the event, and we have seen that already when transforming an almost sure convergence into sets, that the points of omega such that xn of omega divided by n converge to 0, that this, if I want to prove, so what does that mean? That means that for all k larger than 1, and for all n larger than 1, the union for m larger than n, for all k, there exists an n such that for all m larger than n, xn divided by n in absolute value, it's smaller than 1 over k. So saying that xn divided by n converges to 0 is saying that for all k, and there exists an n such that for all m larger than n, this quantity with m here instead of n, it's bounded by 1 over k. So I want to prove that the probability of this event is equal to 0, so I have to prove that the probability of this event is equal to 0, and to prove that this probability is equal to 0, it's enough to prove that for all k, the probability that there exists an n larger than 1, m larger than n, that xm divided by m is larger than 1 over k, that this probability is equal to 0. Right? If I can prove that this holds, this means, well, that this intersection is of course contained in this set. So if I can prove that this is true for all k, I can also, it follows that this event has probability 0, and therefore this event has probability 0, and this is what we want to prove. So in order to prove this, I can replace k by epsilon. So what we need to prove is that for all epsilon, the probability that this probability is equal to 0 for all epsilon positive. And what we are going to do is to prove that the complement has probability 1, so this is equivalent. And the complement, you see, when I take the complement, is, so it's enough to prove that the complement. And what is the complement? The complement is that xm divided by m larger than epsilon infinitely often it's equal to 1. Right? So I have to prove that for all epsilon positive, the probability that xm, so what is the complement here? It's the intersection of all n, the union of m of the complement of this event. And this is exactly that xm divided by m, it's larger than epsilon, infinitely often has probability 1. Well, but this is exactly what we proved, right? We proved that, so this event, it's this one with epsilon equal to 1. So if epsilon, so it's enough to prove that for, we have to prove that for all epsilon positive. The previous argument gives it for epsilon equal to 1, while the same argument will give you that this is true also for epsilon, for any epsilon positive, because, well, if you fix an epsilon, you just redefine your sequence as yn equal to xn divided by epsilon. It's also true that this sequence is a IID sequence, and that the expectation of y1 it's equal to plus infinity, and therefore we are on the same assumptions of the previous result, and it tells us that the probability that yn larger than n infinitely often it's equal to 1, but yn now it's xn divided by epsilon. So this tells us that xn divided by m larger than epsilon infinitely often has probability 1. So indeed, it follows from our previous application that the set of omegas for which xn divided by n converge to 0 has probability 0, and therefore that this set has probability 0. So we just proved this statement that if we have an IID random sequence of random variables and such that the variables have no first moment, so that the expectation of the absolute value is infinite, then the probability that the sequence converge to some real number is equal to 0. So let me conclude this lecture with this remark. So we want to find conditions which guarantee that a sequence of IID random variables converge almost surely to a number m. Right, so this will be called the strong law of large numbers, and we want to find sufficient conditions which guarantee that this average converge to a real number m almost surely. Well, a necessary condition will be to impose that the expectation of x1 is finite. Right? Because if this expectation is infinite, we just proved that this average cannot converge. So this is a necessary condition for an almost sure convergence to a real number. Okay. So when trying to find conditions which guarantee that this average converge almost surely to a real number, we'll need to impose this condition, because we just proved that if this condition is not matched, then the probability that this average converges to a real number is equal to 0. And with that, we conclude this lecture.